Okay, guys, 2.7 graphing techniques, also known as transformations. So what I want to do is I want to go through the basic ones, then later on we'll combine these all together. So the first one I want to talk about is a vertical stretch or a shrink, and you'll find these in your book. I kind of summarized them here. But a vertical stretch or shrink is if A is greater than 1, so we're going to have some real number A, then the graph of y equals a times f of x is a vertical stretching of y equals f of x. Okay? Another way to think about it is the new graph is going to have x comma a times y on the graph. And if you think about it, this makes sense because essentially what I'm doing, y and f of x, same thing, I'm multiplying that y value, right? So that's going to stretch it, okay? Now, if a is between 0 and 1, so if I multiply by, say, 1/2, that's actually going to end up shrinking it. We know that when we multiply by 1/2, it makes things smaller. So it's going to shrink that y value. So then the graph of y equals a of f of x is a vertical shrinking of the graph of y equals f of x. Still, though, that will have the point x comma a times y on it. So when we do these, usually what we like to do is we like to track points because however the points are moving, the graph follows. So that's how I'm going to go about this. So an example on this, let b of x equal absolute value x. Now this b of x, I usually call this my base function, okay? And what it is it kind of tells us it's one of those basic functions we talked about in the last section. Okay, that's my base function, and I'm going to go based off of that, graph the following. So f of x equals 2 times absolute value x. Notice that looks just like what I have up here, and a is greater than 1. So I'm expecting this thing to get stretched vertically, okay? So to kind of squeeze up and go up quicker. So my base function is the absolute value of x, okay? Now, this base function, to get to the next one, I have to write it as 2 times the base function, right? That will give me what I have, okay? So I'm just getting used to writing it in that way, starting with the base function. And notice I have the base function graphed out right here. And what I'm going to do is I'm going to just track a few points. I'll track these 3 right here. So notice that with this new one, if I do x and f of x, if I put in 0, 2 times absolute value 0 is still 0. So nothing's actually changed for this new function. But once I get to x equal to 1, I have 2 times absolute value 1. That's going to be 2. So notice that this point that was 1, 1, now it's going to be 1, 2. So right here. So essentially what I did was I took the y value and I multiplied it by 2. That's exactly what this is telling us to do. Okay. Likewise, if I put in negative 1, I have 2 times the absolute value of negative 1. That's going to be 2. So once again, I've stretched the vertical component of 1 times 2 to right here. So this is now negative 1 comma 2. And now we have a good idea of what my new function looks like. Okay. So here's our f of x. We can see everything, all the y's got multiplied by 2. So if I looked at this, it would be 2, 4. Okay. So that's how you really want to get used to doing this, is to track the points. I generally try to track 3 points and see what's happening. The next one, g of x equals 1/3 of x. Notice that in this case, this a value right here is less than 1. So I'm expecting a vertical shrink. So once again, my base function is absolute value x. So that's what I graphed here in the first place. And I'll track 0, 0, 3, 3, and negative 3, 3. That's just what I chose. And the thing to realize here is to get this, I need to get 1/3 times b of x. And that will give me the thing we want the graph of, right? That's exactly what we want, okay? So, and that's our g of x that we want. So what's going to happen? Well, according to this up here, we're going to have a times y, 1/3 times each y value. So every y value gets multiplied by 1/3. Just to check it, since we're new to these, let's try a few values. X and g of x, 0, 0, once again, does not get affected, and that's fine. Okay. But if I try 3, then I have 1/3 times absolute value 3 is just 1. So at 3, I have 1. 3, comma 1. Notice that this 3 got multiplied by 1/3, just as we expected. So you can probably guess what happens for negative 3. That's going to be 1/3 times the absolute value negative 3 is also 1. So this shrunk down to here. So this is negative 3 comma 1. Well, here is my new function now. So here's our g of x, and it got shrunk by a factor of 3. So that's our vertical stretches and shrinks. Now let's look at horizontal stretches and shrinks, okay? Now this one is slightly different. And it says if 0 is less than a is less than 1, then the graph of y equals f times a of x is a horizontal stretching of y equals f of x. And we'll see that here in a second. And if a is greater than 1, then the graph of y equals f of a of x is a horizontal shrinking of y equals f of x. So now I have the a inside of the function, okay? And we also see that the new graph has whatever x is divided by a, whatever's inside the function, and then the y remains unchanged, okay? So, example, let's take our base function to be x squared. It's one of those base functions from 2.6, and graph the following, okay? So I have my base function, and I got 3 points I'm tracking, okay? And we're going to do f of x equals 1/2 times x quantity squared. Okay, so b of x we know is x squared, and to get to here I need b of 1/2 x. Remember what that tells us to do. Take wherever I see an x here, I'm going to put in 1/2 x. So that's 1/2 x squared. That's exactly what I want to graph. Okay, so I can see, okay, that's the transformation I made. And I know the rule for this here. Since it's less than 1, this should be a horizontal stretch. Okay? Horizontal stretch. So I'm expecting this thing to go like this. So let's see. X and f of x. So let's go ahead. Let's try an x value of 0. Well, then that's going to be 1/2 times 0. Quantity squared is just 0. Nothing new there. But what if I go ahead and I try 2? 1/2 times 2, that's going to be 1. So 2 comma 1. So see how this value right here, that was at 1, 1, stretched out by a factor of 2, right? Notice that the old value of 1 divided by 1/2, if we're looking here, is 2. So you can also think of this in a way as a vertical shrink. A horizontal stretch is kind of like a vertical shrink. So this is the 0.21. And if I try -2, a similar thing happens. Okay. Times -2, quantity squared. And that's also going to be 1. So same type of deal. I have the point -2 comma 1. So this thing just got wider, a horizontal stretch. Likewise, g of x equals 2x squared. I'm expecting a horizontal shrink, okay? So I'll track those same points. B of x is x squared, which I have right here. To get this, I need b of 2x, which I'm going to remember, oh yeah, that's a horizontal shrink. That's going to be 2x quantity squared. Plug a 2x in wherever you see an x. That's exactly what we want. So let's see kind of what's happening here. So I have x, I have g of x. Let's try the point 0. Notice that the same thing happens. Stretches and shrinks don't affect the vertice of the quadratic. If I try 2, okay, I can put that in, and that's 2 times 2 squared. That's actually going to be 16. So what might not be a bad idea is to maybe pick a different point, at least so we can see what's happening. So I'm going to use these 1, 1s and -1, 1. Let's try 1. That's 2 times 1 squared is 4. So now I have 1, 4. Notice how this thing is sort of shrinking over, or you can think of it as a vertical stretch. And let's do -1. That's 2 times -1. That's -2 squared. That's also 4. So we're up here. This is -1, 4. So you can see sort of what's going on right here with our g of x. Okay, so there's our stretches and shrinks.